Okay, welcome. In today's class, we are going to talk about sensors and actuators. Um, and we are going to look at different types of systems that are used in robotic application. And this topic is fairly standard and straightforward. So what I'm going to do is I'm going to review this quickly. And then if you need more details or if you have any further questions, my recommendation to you would be to quickly read through the textbook. So what are we going to discuss in today's class? We are going to talk about different types of actuators. Uh, some of them are, we will talk about electric motors, we'll talk about servo motors, we will talk about stepper motors, direct drive motors. We'll also look at hydraulic actuators, we will look at pneumatic actuators, and there are some novel types of actuators that are used that we can talk about. So next thing is, what are the different important characteristics of uh, different sensors? So most important thing in terms of robotics application, power to weight ratio is super important. Then stiffness versus compliance is important. So what do we mean by stiffness? Stiffness means how stiff the material is, and compliance means how soft or compliant the material is. Many a times what we need to do is we need to change the power characteristics. For example, sometimes we have high speed and low torque. Sometimes we need low torque and high speed. So these characteristics can be changed using some type of a gear reduction. So when we look at power to weight ratio, for hydraulic systems, which is like you have a fluid, you have some type of a hydraulic actuator like a piston cylinder, you have a pump, that is very high. So power to weight ratio is very high. The power units that you need to run the hydraulic systems are quite heavy, and and then the thing here is the whole system or the whole robot becomes bulky. A classic example is if you look at the Boston Robotics Big Dog version, the old version. So basically, nowadays, what they did is they moved on from the 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 hydraulic system. Now they are using electric actuators. Now for power to weight ratio is medium for electric motors, and power to weight ratio is lowest for the pneumatic systems. And that is the beauty of soft robotics. So what is happening is you see this lot of research going on in the areas of soft robotics, and that is their claim to fame. Like those soft robotic systems are light, and then you can actually, they are super compliant, so they can be used for rehabilitation purposes, wearable robotics, and so on. Now, next important part that we have to address is what is stiffness and what is compliance. Now, stiffness means the system does not deform very quickly. Uh, there is some deformation, some stiffness, some springiness included, but still it is not very hard. They actually, the problem with stiff robots is when you are looking at a manufacturing type of environment where a human is interacting with robot, a very stiff robot can actually hurt the human being. So what you need to do is when you are looking at the robot that is working alongside of humans, you need to make sure that the robot is operating safely and cannot hurt or hit human. Many a times what they do is they add something called as the selective compliance, which means you have either a geometrical configuration or some type of an electric configuration that actually would ensure that you have the compliance that is desired for a particular operation. Then again, please try to understand uh, power is given by product of torque times speed. So if you have high speed, then clearly you will generate low torque. But if you want high torque, then the speed would go down. And this approach is used in a lot of applications such as electric motors. And there we use gear reduction. But when we use gear reduction, what happens is you are adding a whole new transmission. It increases the number of parts, it increases the weight, it increases the cost. With gears, you have additional backslash, you have space, it generates more noise, more inertia, and more maintenance. Now, again, the thing here is depending upon the inertias of the gear, you need to take into account those inertial effects when looking at the dynamics of robot. Now, if you were to compare different types of actuators, if you compare hydraulic actuators, positive signs are it's good for large robots, high power to weight ratio, stiff system, no reduction, can work in a wide range of speed. You can have basically something called as the lock in place. So it's self-locking, but the problem is it can leak. It may not be good for the application where you have clean room requirements. It can also catch fire. It requires pumps, reservoir, motor, hoses. It can be expensive. It requires maintenance. You have to worry about the oil viscosity changes, and the dirt or debris would cause that system to malfunction, and high torque, high pressure, and high inertia. If you look at the electric systems are usually good for all types of robots. They have better control, you can get better precision, more compliance, reduction ratio, you can actually reduce, they can be used to reduce inertia. They do not leak, they are good for clean room. They are more reliable, and again, they are spark free, so you can work in an environment where there are explosive gases. Stiffness is low, you need reduction gears, there is an issue with backlash. And if you have a motor, if the motor is freewheeling, which means it kind of runs under the load, then you need some type of a braking type of attachment. Next thing is if you were to use the pneumatic actuators, again, there are some good parts, there are some bad parts. Many components are usually off the shelves. The components are reliable, no leaks, nothing. It's inexpensive, but low pressure, good for off and on-road application. It's a compliance system. The unfortunate part is it's noisy, but you need pressurized air filter, and then difficulty with linear control. So you need special proportional type of valves for the control, and so on. So that is very important when you choose what type of algorithm or what type of robot you want to use. You have to kind of look at the complete range of operation and then choose the appropriate robot. So when you look at hydraulic actuators are used when the requirement is basically you want to have a very strong system. So force is equal to pressure multiplied by area, and in rotary systems, if you want to find out the torque is dA is equal to T times dr, and what you do is if you perform the integration, then you will see that you can find the value of torque, which is the average area multiplied by the pressure. And then you can find out the flow rate, The flow rate is volume divided by time. So you can get the equation for the flow rate. A hydraulic system comprises of a linear or rotary actuator, hydraulic pump, electric motor, cooling system, accumulators, servo valves, check-in valve, sensors, and filtering system. Next thing which I want to talk about is, if you look at a power steering system of your car, it is a simple hydraulic system. So you have a power steering pump, you have a servo valve, which depending upon the motion of the steering wheel excites the servo, extends or retracts, and you have a sensor, maybe a potentiometer or an encoder, that actually looks at where the track is and then basically controls the motion. Pneumatic devices are similar to hydraulic systems. We use pressurized air, low working air pressure, which means a lower power to weight ratio. The problem with air is compressible. So unlike hydraulic system, the hydraulic of its liquid is not compressible, but that is used for insertion purposes and half degree of freedom actuation. It is simple, rugged, it is inexpensive, and it's actually safe. And even if it leaks, you are leaking air, so it's not a problem in a clean room environment. So the next type of actuators that are commonly used are electric motors. There are different types of electric motors. You got AC motors, you got DC motors, you got stepper motors, brushless DC motors. The basic principle is you have an electromagnetic force, and if you have a current that is going through the conductor, and that conductor is placed in a magnetic field, that conductor experiences a torque. And if you use something called as a commutation, where you make sure that you're rotating, swapping the poles, so that the direction of torque is changed or direction of force is changed, so that the torque is continuously applied, you will get a continuous motion. Now, commonly used motors are AC motors and DC motors. DC motor speed control is easier. You can change the voltage, or you can change the amount of current that is passing through, and that will change the speed. AC motors, the speed is the function of line frequency. There could be brushed motor, there could be brushless motor. So brushless motors are simpler and they last longer. The other thing is heat dissipation. AC motors dissipate heat more efficiently. They can work with higher current without damage. Okay. So next is, so the important part for the DC motors is, how do you dissipate the heat that is generated from the DC motor? Now, it is important to note that if you have a DC type motor, the rotor or the part that rotates gets hot, because you have the brushes, you have the commutation, and the rotor winding is on the rotor. So basically I square R type of losses, they happen in the rotor. But in the AC type motors, the heat is generated in stator. So what you have is, you have this air gap, motor body, you have stator, and you have the rotor winding, and you have to be careful when you design a robot. So for an example, if you are going to use a robot with AC motors, you can actually come up with a better heat air ventilation that will dissipate the heat than the DC motor, because DC motor, the rotor is enclosed. But in that case, you add an additional fan or something on the cage, that will help dissipate the heat. Now, again, heat generated is function of the winding resistance multiplied by the square of the current. As the winding heats up, the resistance increases. That increases the heat further. So you want to be careful about the heat that is being generated over the period of time, because as the winding heats up, it gives you a detrimental effect. The resistance increases, that increases the heat generation. Now, one thing just to understand that motor is a mechanical component and an electrical component, which means a mechanical system interacting with electrical system. So you need to be careful about the impedance of the system, also, and also you have to be careful about the mechanical modeling of the system. So strength of the magnetic flux is negatively affected by heat, reducing the torque and requiring additional current. Heat dissipation typically increases with temperature as the temperature increases. And these are the models that are used. So DC motors are quite common, that are used widely in industry. They are actually quite reliable and relatively powerful. And the other important part in the DC motors is the stator has a permanent magnet, or sometimes you can use electromagnet, and brushes and commutators are used to change the polarity of the system. So this is something very, very important, that whenever you are using the DC motor, you want to be absolutely sure is that you're okay with the commutation, you're okay with occasional arcing at the brushes, and so on and so forth. But again, on the other hand, compared to the advantages, you have a lot more advantages, and as a matter of fact, it actually is dictated by the application. So if you look at the governing equation for the DC motor, it's given as torque is equal to Kt divided by R multiplied by V, which is V is the applied voltage, and you have Kt squared divided by R multiplied by omega. And as you can see that this equation is shown over there, you have the torque on the y-axis and speed on the x-axis. And there what you can see is there is a maximum value of torque when speed is equal to 0. And that is called as the stall torque, which means the maximum amount of holding torque that motor can supply. And then other thing is the maximum speed. So basically, what is the torque at the maximum speed? And clearly, torque at the maximum speed is very, very small, very close to 0. So you can see these torque and speed curves. Nowadays, we are moving forward to the something called as the pancake motors, which are like they look like pancake. These are low inertia DC motors, and they are used in a lot of robotics applications. So you will see them used widely. Next is frameless motors. And in the case of frameless motors, the advantage is you actually incorporate this motor as part of the joint, which means this motor becomes the integral part of the robot. And that is a good thing and a bad thing, which means if you want to replace the motor, you will have to take the whole robot assembly apart. Or the good part is basically you are saving the weight and you have the direct integration with the system. Now the next part is you have AC motors. So it could be a permanent magnet or the cage. The stator will have the windings and there are no brushes or commutators, and changing the flux is provided by the AC current, and speed is the function of line frequency, and it can dissipate heat more favorably than DC motors. It's more powerful, and reversible AC motor work with center tapping. So what it means is you have another tap in between that can do the center tapping. Brushless DC motors, Now, believe it or not, they are commonly used in computer hard drives. So it's like the sort of middle ground between the AC and DC motors. You have three sets of electromagnets as shown in the picture. They are 120-degree apart. Rotor is a permanent magnet. And thing is, you need to add some type of a sensor like a Hall effect sensor so that the appropriate switching can happen. And each coil is energized when the rotor reaches a specific location. And you have the sensor, the Hall effect sensor, that can actually control the rotation. Speed can be controlled as a DC motor, but you have the characteristics of an AC motor. Now, there are some direct drive motors, wherein again, the construction is very similar to the brushless DC or stepper motor. They deliver very large amount of torque at very low speeds. And typically a voice coil is used as a direct drive actuation for low torque, but high resolution. Now, servo motors, probably you have seen this word used again and again in a lot of applications. So servo motors, like basically what you do is you add some type of a feedback, like an encoder or optical encoder or resolver, something like that. So the principle is, at the speed of the rotor increases, the back EMF increases. At the nominal no load speed, the back EMF current is equal to the supplied current. When the load is applied, the speed decreases and it creates the net torque. And in servo motor, the speed is measured and is adjusted to achieve the desired speed. And the feedback is also used to measure rotational position and stop at a particular location. So this is how a typical servo motor looks on the right hand side. Again, the same relationship, but servo motor is a closed loop system because you have a controller, you have some type of a feedback coming from the motor, and what you do is you basically use some type of a PID control, either for the velocity or you can use that for position-based control. And in our next class, we are going to spend a lot of time on control, but I would encourage you to look at this closed loop system that actually talks about the feedback. Other commonly used motors are stepper motors. They are quite versatile, quite robust, but they need a drive circuitry. Unfortunately, in stepper motors, there is no feedback, but I have seen some folks adding some type of a feedback, either based on the linear motion or either based on the rotary motion. You add a feedback and the stepper motor can run in closed loop. Each step provides a known angle of motion. And again, unless there is an issue with the controller or the step is missed, speed and position control is easy. They come in a different forms, principle of operation. Stepper motors have soft iron or permanent magnet rotors, and their stator house multiple windings, and it's similar to the AC type of motor. So how does it look? So imagine you have this rotor that has north and south poles, and you are going to excite the coils to change the polarity of the electromagnets. So as you can see, we are switching. And as you switch, the rotor changes its orientation. And if you make that switching fast, then the inside rotor would start rotating. If you want a half a step, then you can excite in between, and then at that time it will be the rotor will be stepping through the half. Nowadays there is this can stack motor wherein you have alternate north-south poles. Basically they are based on Halbach array, and this is how it looks like. If you look at that, what you have is you can have stator that is made up to 4 poles, and again you have this staggering pattern, and then you do alternate coils actuation, and basically that causes the rotation. And again, so just similar to stepper motor, you would have some type of a sequence, and you would be sequentially turning them on, off, and so on. And basically you get a continuous rotating pattern. Each arc and each sequence will rotate in one step. And again, if you want to achieve half stepping, it can be done as follows. Again, you have this stepping pattern and you can use it. Sometimes, depending upon applications, you can use hybrid stepper motors. They are made up with two coils. They could be center tapped, independent windings. You could have permanent magnet rotor with two collinear cylinders, one at north, other end at south. Rotor and the stator poles have all cut teeth, and then they are basically offsetted by the other half. And again, depending upon how you align those, you can get a very finite stepping. So basically, you can measure a small step or a large step stepping. Now, similar sequence again of cam stack motor causes the rotating flux. It follows the small angle, and you can actually control how many switchings, how fast, and that gives you the angle of rotation and speed. And again, there are something called as unipolar motors, bipolar motors, or bifilar motors. So unipolar motors require only one power source. Usually they can't run in half steps, need more power. Bipolar motors require more power source. It can run in full or half step modes, and motor develops full power. In bifilar motors, the coils are center tapped, one power source is needed, can run in full and half steps. There are different winding configuration. You have a 4-lead configuration, you have a 5-lead configuration, you have a 6-lead configuration, and you have an 8-lead configuration. Now the torque and speed characteristics of stepper motor, as you can see that as speed increases, torque drops down. At holding torque, you have the zero speed maximum torque. And again, you have to take into account the effects of inertial loads, back EMF, and so on and so forth. Now, sometimes what you have is you have something called as the flow back. So think about it like every electric motor is like a generator. So what you want to do is you don't want, whenever you have certain changes, the motor is acting as a generator and it's feeding the current. So you need to allow it to freewheel. So you can add some type of diodes to make sure that the current is only flowing in one direction. In the case of micro stepping, you can actually turn coils on and off in mini steps, starting from 128 all the way to 512. 50,000 steps per revolutions are also possible, different switching patterns, and it's a whole controlling the stepper motor and coming up with the algorithm, closed loop algorithm. It's a whole new area of research. So typically stepper motor controls is done using MOSFETs or stepper drivers. You can use output ports, you can use power transistors if you need, and basically control the stepper motor. Again, these chips are ASIC, application specific integrated circuits. They are designed and built by the manufacturers. So you would see there are analog devices, stepper drivers, there is microchip, there is ST. These stepper drivers, they are like MOSFETs, they are transistors, and you turn on and off very fast to achieve that sequence. If you want to use the microprocessor controlled, what you need to do is you need to connect your stepper motor driver or stepper motor chip with a microcontroller or microprocessor, and it will change it will send the bit sequence using pulse width modulation, and that will actually fire the H bridge and basically run the stepper motor. Again, you need, it's not one thing fits all requirements. Depending upon your requirements, you need to make the changes to the power conditioning. Sometimes you have to use the transistors, sometimes you need to incorporate diodes, and so on and so forth. So this is a simple H bridge control. As you can see, there are transistors or switches. If you think about a transistor is like a switch, a mechanical switch, but it's like an electrical switch. So you can turn on and off transistor, And as you can see, there are 4 transistor switches: S1, SW1, SW2, SW3, SW4, and you can actually supply the voltage. You can turn them on and off and change the direction. Okay, so if you want to attach that with a microprocessor, so you have transistors. You have transistor 1, transistor 2, transistor 3, and as you can see, the motor is connected at the leads A and B. And because the way these transistors are configured, this looks like an H. That's why it is called as an H bridge. Now, there are a lot of exotic actuators that are used in robotic applications. You can have magneto-resistive, you can have shape memory, you can have electroactive polymers, and many of those are used in robotics application. Another important thing that you will need to take into account is adding transmission. So many a times the motors, they run at very high speed, low torque, but you need some type of transmission that will take that high speed, low torque power and convert that into low speed, high torque power. So as you can see, you can use planetary gear trains, you can use harmonic drive, and you can use different type of speed reductions. So to make sure that it is meeting the applications that you need. So this is a very simple topic, but what I want to do is I want to take this opportunity to briefly talk about the next topic, which is we talked about actuators. We can do the same thing with sensors. Please understand, sensors and actuators is like eyes and limbs. So sensors are eyes and limbs are like hands and legs. So let me, since we talked about the actuators, let me quickly talk about the sensors. And this chapter is very easy. Mostly it's like a self-study chapter, but I would encourage you to review the chapter as and when necessary. So sensors are used for feedback. You can have internal feedback or you can have environmental sensing. Just like animals and humans, we have eyes, ears, those are different types of sensors. A huge array of sensors is available for measurement of different type of phenomenon. And we'll briefly talk about few sensors, not all of them. So where do we use sensors? We need sensors to measure position, velocity, force. We need to know touch, like capacitive touch, like your touch screen. We need tactile sensors. We need proximity sensors. We need to find the range, like LiDARs. We need vision, camera. We also need the sniffing, testing, speech, and speech recognition. So think about Amazon Alexa or Siri. What are the different sensor characteristics? You have cost, size, weight, output, interface, resolution. And please understand, we have bits on and off. So resolution is basically 2 to the power n. So if you want to find out the resolution, you take the full range and divide that by 2 to the power n. And different characteristics: sensitivity, linearity, range, response time. Again, it is expressed 95% of the total change. And if you look at the response time of 63.2% is called time constant. Rise time is the time needed to achieve 10% to 90% of the final output. And settling time is between 0% and 98% rise. So what type of sensor you use, it completely depends upon what your requirements are. What are the different characteristics? Frequency response, reliability, accuracy, and repeatability. So as you can see, it's a target not hitting the target. It's inaccurate and not repeatable. You are hitting somewhere consistently, but that is not the target. That means it is inaccurate but repeatable. And last thing, you are hitting the bullseye, which is accurate and repeatable. Important sensor that is used in robotics is the potentiometer, which is used for internal feedback. You can have a rotary potentiometer or you can have a linear potentiometer. They can be used alone. They can be used with other encoders. You can have analog output. You can have single or multiple turns. You can, if you have wire wound, then output would be stepwise. Sometimes what you do is you can actually, you have some type of a conductive polymer, the output is continuous. So here are some say other sensors like encoders. You get digital output. It produces a signal for each small step of movement. The disk is divided into small sections. It's opaque. You have option whether you want to do opaque or transparent. You can do linear or rotary, and sometimes you can do light source, LED on one side, or you can have maybe some just using the Hall effects. Incremental encoders, so sections are equal and repeating. Each sensor repeats equal angle of rotation. Only the change in the position can be measured, not the absolute position. And the direction cannot be measured unless there are two slots. So basically, if you want to know whether you are rotating clockwise or counterclockwise, you need input from two. Again, for incremental encoders, again, you can do either some type of an interrupt depending upon the leading edge, trailing edge, or you can actually design your algorithm. Absolute encoders, they measure in terms of absolute value. It's not relative. You can measure the absolute position, and you can use it either a binary or a gray code. So this is the gray code. So basically, it can be used as 0, 0, 0, 0. You can see the binary code. You can see the gray code interpretation, and that is commonly used in robotics. So typically, you would have some type of an encoder that is attached to the motor, and you can, if it's an absolute encoder, you can get an absolute rotation, or if it's a relative encoder, you can get the relative motion. Another interesting sensor is linear variable differential transformer. The idea is simple. You have a primary coil, you have a secondary coil, and you have the core that is in between these two that is movable. So depending upon the location of the core, you can actually find out the voltage on the other side. Again, it's AC. So what you want to do is you need to have some type of signal processing that will convert this AC voltage, differential AC voltage into the displacement. So there is some signal conditioning that is needed that will take this relative displacement and then convert that into the relative motion. Relative voltage into the relative motion. There is something called as a resolvers. Again, they are rotary sort LVDTs. So they are used for measurement of angular motion. It's also a transformer. You have a primary coil, you have two secondary coils, and then basically you measure the phase difference between primary and secondary, and that gives you the resolution of angle. You can also use something called as LMDT, which is magnetoresistive, magnetorestrictive transistors, wherein what you have is you have a magnet that is going back and forth, and then you actually measure that moving part to a magnet, and that kind of gives you the position. Hall effect sensors is like conductor output carries the current that changes in the presence of magnetic field. Hall effect transducer is analog and it gets converted to digital application. It is used in many applications, including sensing of the position and permanent magnet motors and DC motors. Another important aspect, especially if you are looking at the aerial vehicles or the ground vehicles that are used outdoors, use global positioning system. So global positioning system is a satellite navigation system. You need 4 satellites to resolve X, Y, Z, and finally the time. So you have 4 variables: X location, Y location, Z location, and then what you want to do is you want to measure the time. So you need at least output from 4 different satellites, but typically you get output from a lot more satellites to get a better resolution. So again, velocity sensors, you got encoders, you got tachometers. Encoder, basically they don't work very well at very slow speeds, but they were quite well in the range that they are designed, like medium speed. Tachometer, again, it's an analog output sensor, so that can be used. The next thing is, if you think about it, you got other differential sensors that are used for velocity measurement. And basically, again, there are a lot of different applications, but what you do is you can actually use a potentiometer with conductive polymer, and that will give you the sensor output. So you can actually get the velocity, integrate the velocity, get the position, and so on. Then another force sensor is used in strain gauges. So adjust R4 as the piston bridge until the galvanometer central voltage is 0. So please try to understand the basic principle is very simple. The resistance changes as the length of the resistor changes. And the strain gauge, what is going to do is it's basically going to change the strain gauge resistance, but that strain gauge resistance is so small that what we can do is we cannot use the regular voltmeter or ohm meter or multimeter to measure that change in the resistance. So what we need to do is this teeny tiny change in the resistance now that needs to be converted, the teeny tiny resistance needs to be converted into something meaningful or something measurable. So what we do is we actually use something called as Wheatstone bridge network, which is like an amplifier circuit that actually converts this teeny tiny change in the resistance of the strain gauge and converts that into something that we can measure. So that is very, very important. So next thing is if you want to measure the strain, there is a concept which is called as apparent strain. So for an example, even though there is change in the temperature, the strain that is measured by the strain gauge would change, and we really don't want that. So basically there is this apparent strain that we need to compensate for, and that is something that we can do electronically, or you can use some type of a dummy sensor for compensation, and then you can use that for your application. Again, there are torque sensors that are used. So again, application is a strain gauge, but the torque sensors, the strain gauges are mounted in a particular configuration that is called as a rosette. So they are mounted in a particular orientation, and that actually gives you the differential forces, and these forces can be used to calculate the torques. And again, there is a little bit strength of material and mechanics of material, that type of concept that is used to convert the strain gauges output into the torque. And it's very important that where these strain gauges are located and how well they operate. Again, there are touch sensors and tactile sensors. So think about touch sensors as capacitive touch screen that are used widely in phones or computers or tablets. And you can use different types of sensors. You can use piezoresistive sensors, or you can use the optical sensors, and you can use different combinations of sensors depending upon the applications that you are looking for. Sometimes you can use a simple proximity sensor. There are two types of proximity sensors commonly used. One is a magnetic sensor, another one is an optical sensor. So magnetic sensor is activated only when it is close to the magnet. Optical sensor is activated when the light path is interrupted. You can also use something called as an ultrasonic sensor. So ultrasonic beam sends signal, and that's get reflected, and you can measure the time it takes for the reflection to achieve, get back to the emitter, and then you can actually find out the distance. There are different types of proximity sensors. There is inductive, capacitive, and eddy current. So inductive based on direct metal contact, capacitive reacts to the presence of object, and eddy current are based on the back EMF. Range finders like lidars, they are used for for using lasers. So you can use these laser distance traveled or reflected from laser, just like ultrasonic sensor, to find out the location. They are commonly used in point cloud mapping and applications where we want to get perception. And few common methods are triangulation, time of flight, or lapse time. So this is a rangefinder application wherein you have a receiver, you have an emitter. So emitter sends the laser gets reflected and then gets received, and then it's only occurs at the particular instance, and then the emitter is rotated until and basically if you have a constant rangefinder oriented in one direction, or you can have a rangefinder that is continuously rotated. And again, you can use either time of flight algorithm or the lapse time algorithm, but at the end, you take that data and convert that into the range output. Ultrasonic sensors are also used for range finding, but resolution is limited, the range is limited, and frequency is beyond or below the human hearing capacity. Nowadays, lidars are used everywhere. Velodyne lidar is shown here, wherein that is used to get the perception of the surrounding. You got the laser that is continuously rotating, and it's again you can get stereo imaging, and you can get a very nice output from the surrounding. So if you see the Google car or driverless car, there is a dome on the top that has the lidar. Nowadays, with advances in natural language processing, you will see these voice recognition systems appearing everywhere, all the way from Siri to Alexa. And again, the idea is they get this word, but then they use some type of a neural network machine learning algorithm to get the context of that word. And you are welcome to take courses in natural language processing either at Sky or at IFT. That will give you some information on how this thing works. Voice synthesizing is also a very important aspect. Basically, you can create words or sounds by combining recorded information or combining the information generated from some type of a network or maybe generative AI and so on and so forth. Another thing is if you are looking at an assembly task, wherein what you have is you have a robot that is putting this peg into a round hole, a round peg into a round hole. You want to have some type of alignment compensation. So you allow this alignment to go on smoothly. So you have some type of flexibility, some type of actuation, some type of compliance at the joint that allows an easier assembly. Again, what you can do is, if you look at kinematically, it's a 4-bar mechanism. And when you study the kinematics, you see where is the instantaneous center of rotation that is at the intersection of those two links. And you can use this type of analysis. And on one side, you see the locomotion mechanism, where is the infinite the center of rotation is located at infinity, which means that rod is going to go in a straight line motion. Another thing is, if you were to look at RCC compliance device, which is basically the combination of both. So you have a 4-bar mechanism and you have a selective compliance. So you will see a 4-bar mechanism on top and you see the joint modulation at the bottom. So with that, we are done with 2 theory chapters from the textbook. And we are only left with one last topic that we will be discussing in next 2 to 3 lessons. That is on the control systems, feedback systems. So we are going to focus on the control systems. but I would encourage you to finish all the assignments, all the lab, and turn in all the homework that is due. I will upload this slides. If you have any questions, I would be happy to answer. Any questions from anyone? If there are no questions, I will see you next class. Thank you very much and have a good night.
Thank you, Professor.